All right, we're going to continue our discussion of circular motion here. Our first example, we are looking at the Ferris wheel on Navy Pier. It's got a diameter of 196 feet, and the Ferris wheel takes about 12 minutes to complete 3 revolutions. So, first, let's draw a sketch showing one rider. So, 2 identical twins. But apparently identical twins who don't like each other because they won't ride the Ferris wheel together. They're on opposite ends. So we have a Ferris wheel, and we have one rider at the bottom, and a rider at the top. And this is Ted, and this is Bill. And the fourth wheel has a diameter of 196 feet. So clearly the first thing that we have to do is get rid of these American units and go with international units. So the radius of this Ferris wheel is actually 29.87 meters. So if we are looking at Bill and Ted here, the first question is, what is the direction of the centripetal acceleration for each of the twins? Well, again, the word centripetal simply means center pointing. So for Ted at the top, the acceleration is pointing inward, and for Bill at the bottom, it is also pointing inward. So the acceleration for each of the twins is both centripetally directed toward the center of the Millennium Park Ferris wheel. Sorry, the Navy Pier Ferris wheel. Free body diagrams for each of the twins. Right, make sure the net force is pointing in the direction of the centripetal acceleration. So if we have Ted at the top, the first thing we do is we circle Ted, and we see that there is a normal force on Ted by the Ferris wheel seat, and there is a gravitational force. So for Ted's free body diagram, we have FG, sorry, this is Ted, and we have gravitational force on Ted by Earth, and we have the normal force on Ted by the Ferris wheel. For Bill, on the other hand, at the bottom, sorry, getting back to Ted here right quick, we know that the net force on Ted must be down because the acceleration is down. It's toward the center of the Ferris wheel. Therefore, we know that the normal force on Ted is less than the gravitational force on Ted. Now, if we consider Bill at the bottom, this is Bill. Well, they're identical twins, so the gravitational force on Bill by the Earth, that's got to be the same as gravitational force on Ted by the Earth. But on Bill at the bottom, the acceleration is upward, so the net force must be upward. So the normal force on Bill by the Ferris wheel must be greater than the gravitational force. Calculate the magnitude of the centripetal acceleration. Well, we learned on Tuesday that centripetal acceleration is the speed squared to the radius. Speed is the distance over the time vector. And the total distance is 2 pi times the radius divided by the period, capital T. So this is equal to I'll include the fact that it says that the problem states that it makes 3 revolutions in 12 minutes. So the period T is equal to 3 revolutions in 1 minute. So the total velocity then is there are 3 revolutions of 2 pi r distance each, and the time for that is 12 minutes times 60 seconds per minute. And it then leads to the speed of the Ferris wheel of 0.782 meters per second. Centripetal acceleration then, A sub c is equal to 0.782 meters per second squared divided by 29.87 meters, and this gives a centripetal acceleration of 0.02 meters per second. Calculate the normal force on Ted and the normal force on Bill if they each have a mass of 55 kilograms. So for Ted at the top, net force is equal to the mass of Ted times the centripetal acceleration, right? That's Newton's second law. F net of Ted is Ted's mass times the acceleration. Looking at the free body diagram for Ted, this is equal to gravitational force minus normal force, or normal force is equal to Fg minus MAC. Which is equal to 55 kilograms, Fg being mg. So this is mass times g minus a sub c. So the normal force on Ted at the top is equal to 537.9 newtons. Looking at Bill at the bottom, the net force on Bill is the mass of Bill times centripetal acceleration. But looking at the free body diagram on Bill, we know that the net force, again, the net force is toward the center. So we have the normal force, F sub n, minus F sub g, because we know that the normal force on Bill has got to be greater than the gravitational force because the net force is toward the center. So the normal force on Bill is equal to Fg plus m a sub c, which is equal to mg plus a sub c. And so the normal force on Bill at the bottom is equal to 540.1 newtons. So this question about who feels the heaviest then is Bill, because the normal force on Bill is greater than the normal force on Ted. Once again, for this problem, our process has remained the same. We've identified our system. We circled the system so that we could identify what forces were acting on the system, normal force and gravity. From identifying our system, we then drew a free body diagram for each. From the net force statement, we were able to determine the magnitudes of these forces that are acting on the system. And then we used Newton's second law to determine the net force. Net force is mass times acceleration, and then that same net force comes from the free body diagram. In the case of Ted at the top, it's greater downward. The net force is downward, so it's Fg minus Fn. And for Bill at the bottom, the net force is greater upward, so it's Fn minus Fg. Okay, back now, we have a 0.75 kilogram ball attached to the end of a horizontal cord, which is rotated in a circle of radius 2.2 meters on a horizontal frictionless surface. So in other words, there is a surface here around which something is rotated on the frictionless surface. So this radius is 2.2 meters. The mass of this ball is 0.75 kilogram. The coefficient of friction on the surface is 0. And we know that the tension max is 55 newtons. Anything greater than 55 newtons, and this cord is going to break. So, circling our system, I'll include the cord here. Circling our system, we know that there is a normal force from the surface on the ball. There is a gravitational force on the ball, and there is a tension force on the ball. So now that I've identified the forces involved, I draw a free body diagram. Here's the ball. F3 is the same as the normal force. And the net force then is equal to the tension. And the net force is also equal to mass times acceleration. In this case, that is a centripetal acceleration. So we know that the tension is equal to mass times v squared over r. So we know that this has to be, that the maximum that this can be is 55 newtons. So solving for this, again, what we see is that there is mass on either side of the equation. I'm sorry, we actually need the mass. Do not cancel that, my mistake. We know that 55 newtons then is equal to 0.75 kilograms times v squared over r. And we're trying to find the maximum velocity, the maximum speed that this ball can be rotated without breaking this 55 newtons. So it is 55 newtons divided by 0.75 kilograms times the radius of 2.2 meters. Is going to be equal to the speed squared. And taking the square root of that, we end up with the maximum speed being equal to 12.7 meters per second. Finally, this is a similar problem to the one that we looked at on Tuesday. In this particular case, we're interested in determining what the maximum speed a 1,350 kilogram car can round a 40-meter turn on if it's a flat road and there's a coefficient of static friction between the tires on the road of 0.65. So from a top-down view, car is on the road, and this radius is 20 meters. So from the side, we've got a level road. And this car is on the road. It's got gravity and normal force, and the centripetal force that is causing it to go around this curve is from friction. Now, here's where I want to make sure that I make clear something that I may not have emphasized sufficiently on Tuesday, and that is that when we are talking about centripetal forces, forces are interactions between two objects, and there is no object known as a centripetal. Centripetal is an adjective. So there is no additional force that is a centripetal force. There is a force, in this case it's a friction force, that is acting centripetally. So F sub C is that friction force. So there's not a centripetal force and a friction force. It is that the friction force is centripetally acting. So centripetal is an adjective. It describes the direction of an existing force. Okay, so for this problem then, F net of this car is equal to mass times the acceleration. And again, given that the acceleration is centripetal, I will note that with a subscript C, and that force is equal to friction force. And as we investigated from the lab, we know that the friction force is equal to the coefficient of static friction times normal force. So mass times centripetal acceleration is equal to coefficient of static friction. The normal force is equal to the gravitational force, so times mg. In this case, I can simply cancel the mass. And what I've got is maximum velocity squared over r is equal to the coefficient of static friction times g, or the maximum speed, v, is equal to the square root of r, coefficient of static friction, times g. And in this particular case, when I plug in 40 meters 0.65 coefficient of friction, and 9.8, I get that the maximum speed is 16 meters per second. I work through the practice problems that are given here as well. Additionally, there are labs that are due. There's a pivot lab that is due, as well as homework. Have a good weekend. I will see you all on Tuesday.